Okay, so let's continue. One important remark, so that the winning strategy is always very weakly dominant. Now, let's quickly go over why it does not necessarily can be said always to be strictly or even weakly dominant. So strictly dominant means that it's strictly better than any other strategy for any for any choice of the strategies of the other player. So for that player, the strategy should be strictly better than any other strategy of that player for any choice of the strategies of the other players. Now it's clearly that you can set okay, a simple example. If you have two winning strategies, then already you cannot say that one of them is always strictly better than the other one. Actually, they're always exactly the same because they always give you the victory. And that's also why it's not even weakly dominant, because to be weakly dominant, you need to be at least as good as any other strategy, and for some settings of the strategies of the other players, you need to be strictly better. But if they are both winning, you are never strictly better than the other winning strategy. So it's not even generally speaking weakly dominant. It's only very weakly dominant, which I remind you means that regardless what the other players do, it's always at least as good to do what the strategy prescribes. And that's true, because the strategy always leads you to victory. So that's a very weakly dominant. Of course, mostly, colloquially speaking, mostly this is also a very a weakly dominant strategy, because you usually can, again, actually, if you don't have at least two winning strategies, then, and you do have some choice, so that you do have more than one strategy, then actually you can say that the winning strategy is weakly dominant, because for any other strategy, well, it's definitely not worse. And since any other strategy is not winning, as we assume, then sometimes it's strictly bad. Now, we cannot, however, even in this case, we assume that there is only one winning strategy and more than one strategy in general for that player. We cannot assume, we cannot say that this this unique winning strategy will be strictly dominant. Because maybe there are some settings of the other players such that this strategy is actually winning, true, but and also there's another strategy which leads to a victory without being a winning strategy in general. Okay, so having mentioned that any winning strategy is a very weakly dominant strategy, let's remember that we prove this von Neumann theorem, which employs Merle's algorithm. Maybe actually that's the name in the algorithm, which is the backward induction which we use in the proof, is actually Zermelo's algorithm, while the theorem is called von Neumann's theorem. I'm not sure. Maybe actually it's not true, so I'm going to use this somehow interchangeably. So let G be a combinatorial game. Then exactly one of the following holds. Player 1 has a winning strategy, player 2 has a winning strategy, or both players have strategies guaranteeing at least a draw. I remind you that the fact that at least, excuse me, exactly one of players win or they get a draw is still very true. That exactly one of those options holds. That's true for a single play. Yeah, it's trivially true that either player 1 wins or player 2 wins, or both players get a draw. However, the fact that player 1 has a winning strategy, or player 2 has a winning strategy, or both players have strategies that guarantee at least a draw, that is something which is not trivial, and that's something we've proven. And that's actually spectacular, I might say. So let's now go to an important example, which is taken from, known, but the presentation is the most taken from what Ron Holzman at the Technion did in his lectures. And the main difference I'm actually exhibiting here or Ron Holtzman did, made from the classical presentation of this game, is that he basically assumed that we break the upper right part of the chocolate bar, or whatever you call this two-dimensional array, while the classical case is that you break the down right, the down right part. Now, it does not matter. Simply in the upper right part, you may use the normal coordination axis, and that's simply that's simply much more convenient. That's why I'm using his approach. I guess, I'm not sure, I guess that's why he used this approach instead of. So basically, this idea of breaking something off is actually not my picture. I used it from Wiki, but in Wiki they use the reflected picture. Reflected with respect to the horizontal line. Okay, so finally, whatever I just said before, it's simply technical details. So let's get to the game. It's a simple combinatorial game. So assume that we have this two-dimensional array of indices. So all the all the integer numbers between 0 and m minus 1 and minus 1. So that's an array of m over n numbers. M in horizontal, m it's breadth m and height n, or it has m columns and n rows. See my screen. So this is m, here m is 5, and this is n, here n is 4. And the original array lacks this left downmost square, where you have this spider or whatever drawn. That one is out of the picture. So they actually should have just removed it, but whatever. So that's this array besides 0, 0. The indexing begins from 0, 0. And this is called an M and Chomp game, by the way, denoted by GMN, probably because of the inventor's surname Gale. When you assume M and N above at least 1, and the sum is at least 3, so it's not only this forbidden square, which does not exist, but it's at least the smallest option is like this and this, or this and this. So there is at least one thing to break off. And you have two players, whites and blacks, like in chess, with the same meaning. So the whites start moving and the players move alternating. So white, black, till they finish. And now at step P, the active player, this move step, picks some still not removed square ij from M, so something which still is in this array, this step. It does not necessarily mean that everything which is to the right and upper will also exist, but at least this one exists. And then the next array is what we had when we had chomped away ij and all which is to the right and up. So all those scales, such as k is at least I and l is at least j. So in this example, right, 0, 1, 2, 3, 4. Excuse me, 1, 2, 3, yes. And this 0, 1, 2. So 4, 2. Let's say that the white starts with 4, 2. So this square and everything which is to the right and upper. So these two squares get chomped off and get broken off of this chocolate bar. And that's the action. Now, if the second move of then the black, let's say, chooses this square, and only this square will be removed because this has already been removed. So if the second player chooses this, then this will be removed, but those two squares have already been removed. So clearly, I hope you see my mouse moving. So clearly, you can sometimes like swallow what the other person has done by choosing to remove more. Anyhow, so you pick a j which is not removed yet, and you remove everything which is to the right and upper, and that's why this coordination axes, these axes are useful here, because we simply move everything which is at least I and j, and that's how they move alternated, and the player which is able to move last wins. So if I'm the last one to move and then you are not able to move, then I win. Or in other words, the player who is the first one who is stuck, is not able to move, which basically means that the only square left is this one, which has not existed already anyhow. Nothing is left, in other words, that player loses. So, since the number of, you always choose some square which has not been removed, that means that you strictly decrease, you remove at least one square. The number of the squares on this array strictly decreases, so the game is finite. It takes at least m times n minus 1 rounds to play it, yeah. If you just remove 1, 2, 3, 2, 2, 2, 2, 2, 2, 2, you can actually play indeed in this order, and then you're going to remove one square at a time. So you can play exactly m times n minus 1 rounds. Now these are win-lose, so there is no draw. Combinatorial game. Why is it combinatorial? So I remind you, combinatorial game means it's win-lose. Every play is finite. Clear is here. It is, as I've said, most m times n minus 1 rounds. Moves, I should say. And the game is not, there is nothing random, and there is perfect information. So it's a combinatorial game. And I remarked, why do we need this or rational why the am0 does not have 0, 0? Because if it did, then white would simply trivially be able to win. It would just pick this square, delete everything, and win. Now, since the square cannot be picked because it does not exist anyhow, you are not able to win. By the way, there are generalizations for more dimensions of this game. Okay, nothing, we don't go there now. So, the Zermelo phenomenon, or whatever you call this theorem, implies that either white or black have a winning strategy. There can be no draw, so there are only two options. At least exactly one of those options has to hold. And the question, of course, is, so who has a winning strategy? In which case, maybe M is whatever, and N is then something happens. So who and when does have a winning strategy? So first of all, we know that we can actually give a constructive answer to the question when m is equal to n. So when we start with a square with a broken, it's a broken square, because we have this non-existent, so it's a square in the sense that the whole array is square, m equals to n. And if you look at one part of this array, one square within this array, this 0, 0 doesn't exist, so that's why I call it a broken square. So if m is equal to n, and of course then have to be at least 2, because their sum is at least 3, and then whites have a winning strategy, and moreover, we can actually give a constructive answer. We can actually pick a constructive, we describe, have a prescription how to act. Not only that it exists, but we actually can give. And the intuition is that we are going to enforce symmetry. So one is why solve is going to start by an action which brings to symmetry, and then enforce symmetry, which will lead that it always can restore symmetry, and thereby always wins. Well, the details are as follows. So the strategy W starts with picking y1. So that's the square that W picks, and that's all that gets deleted. And we are only left with those two rows. One row, so 1, 2, 3, and so on till m minus n at height 0, and 0, 1, 0, 2, 0, 3, and so on. This So there are basically two lines, squares left. With this one, the horizontal and the vertical line. Formally, after time 1, or after time 0, at time 1, I remind you that we sometimes wrote the dimensions of A below, which they don't change, but the same as the dimensions of the game, but the time is here in the parentheses, and we actually should use that here too. 1 second, please. So going back, W chooses 1, 1, and then you leave two kind of two rows, not kind of two strips. So one is 0j, so j goes from 1 to n minus 1, 0, 1, 0, 2, and so on to 0 n minus 1. Another one, the horizontal, it's excuse me, that was the horizontal. The vertical, no, that was the vertical, because we ran over the vertical dimension j, and now we run over the horizontal dimension. It's I0 when I goes from 1 till n minus 1, which means that you have this 1, 0, 2, 0, and so on till n minus 1, 0. So that's what we do, and then whatever B does, B has to chomp from exactly one of those lines. W just restores symmetry. So formally, if B picks 0, J, then W just picks J, 0. And if B picks I, 0, then W picks 0, 1. So here, formally, if B decides to go to this thing and go and kill all those, then W kills all those. And since we assume that it's a square, we assume that it's the same numbers. We had a symmetric state, and we constantly W constantly basically recovers the state. So whatever B does, W recovers. Then that allows us to prove inductively that after W is moved, there is some case such that we already again have two symmetric parts of these stripes. So 0j when j is from 1 to k, and I0 when I is from 1 to k. That's the same case. And that means that W can always move, as we discussed above, symmetrically, and therefore W moves. So we are given a concrete strategy, which we have also seen is a winning strategy. That's a constructive answer. Now, if M is not N, that idea generally does not work. Since if W gives a start with, it doesn't work at all. So it's not a winning strategy, because if W starts with taking 1, 1 and all what is to the right and up, or all those ij such that I is at least 1 and j is at least 1, then B can complete the symmetry, because there was no symmetry. Now B can act and complete the symmetry, and then do what the whites do. So white will have to break the symmetry, and black will restore the symmetry. White breaks, black restores, and thereby you will win. So for this strategy, there is a strategy of B which can cause W lose. So that's not a winning strategy. Now, is there another winning strategy? Actually, yes. And we can prove that W does always have a winning strategy in any GMN, in any kind of such a game, in any Chomp game. However, we don't prove this constructed. We just show that there exists a strategy. And the intuition is that we basically use a technique which is called strategy theft. So we prove by contradiction using this strategy theft technique, which goes as follows. So assume to the contrary that W has no winning strategy. Now, unlike what we had in the previous case, here, unlike the proposition, which we do have a winning strategy for the white when we start with a broken square, but we didn't have to know that it exists. We knew, but we didn't have to. We just showed it. Here we do use the fact that the Zermelo's theorem imply that exactly one has a winning strategy, and thereby, if we assume to the contrary that it's not white, it has to be the black. Okay. So the B player has some winning strategy denoted by tau. That's our assumption by contradiction. Now, let us now construct a strategy for W, which works as follows. W starts with m-1, n-1. So it basically chomps off the right uppermost square. And that's what we have. So simply the square, the original square, doesn't have this square, the left lowermost, and now white has chomped off the right uppermost square. Now, then tau prescribes B, excuse me. It's not what W does. It's if W did that, then tau would prescribe B to react by choosing some ij. Now, and then what we say W, now what we do is choose this ij that tau would prescribe B to choose if you chose this m-1 and so you know that again we do it. We don't know what exactly this tau is, but it claims that there is some tau. That's what we said. And then for this move of W, tau would prescribe B to choose some ij. So let W start by choosing this ij. There is such a choice. Now, please pay attention that this ij results in something which is exactly what would happen if W just started with that. With, excuse me, m-1, n-1, and B reacted by tau. That's by construction. So W now made the remaining array what else to be exactly what would happen if W started by chopping off the right uppermost square, and B just did what it should do by tau. And then, since now it's B's turn to play, unlike what would happen if W started by m-1, n-1, and B reacted, because then it would be Y to play. So now Y is actually in the position that B would be if W started with this m-1, n-1, and B followed its strategy, its winning strategy. And now W basically can react on B's move. Again, we don't know how, but there is strategy, we assume, such in the way that tau would react on that move by W. Because now W has basically switched the role for the same position on the board. Now, since tau is a winning strategy for B, the described strategy guarantees that W now wins, because W has managed to move to the position that B would have moved. Now, this is not a symmetric game, of course, because the strategies are actually not the same. by definition simply white starts before the black, but it's symmetric in this sense. And so we have basically managed to construct a strategy without saying exactly what to do, but saying that we can, if there is such strategy tau, then we managed to construct such strategy for W, which always makes it win. So W also has a winning strategy. Now, since both players cannot possess winning strategies, then we arrive at a contradiction. And please notice that W has a winning strategy. We didn't say that W has a winning strategy because it wins against B playing something. No. B here played whatever B wanted. W simply said what would happen if B played this tau, and then, but here, the strategy we constructed for W won against any strategy B actually played. Okay, so we showed it's a winning strategy, and then it means that W has a winning strategy. B we assume has a winning strategy, so it's a contradiction, and thereby we go back, and so the assumption that W has no winning strategy is wrong. So W has a winning strategy, we don't know which, so we managed to steal the strategy of B, and we could do that because B's reaction on picking m-1, n-1 swallows this m-1, n-1, and thereby we managed to basically be after the first action of A in the same situation as it would be after the action of B. That's why we managed to do it here, but not, for example, in chess. So in chess, it's not what we can. Well, chess is different in many aspects, but we're just saying is that this technique works here for this reason. And now let us recapitulate this first chapter on non-cooperative games. So we defined extensive games, including randomization and imperfect information. We defined subgames. Remind you, the subgame is simply the subtree, whatever happens in the subtree, and the information is imperfect, and we may not cut information set. And now we defined what it means to be a winning strategy, simply a strategy which always causes the player to win, regardless of what other players do. It can be, by the way, I said that every winning strategy is a very weak, dominant strategy. It came that there is no winning strategy, but still there is a very weak dominant strategy. Simply that the best option you can get is not that you always win. For example, that you sometimes have a draw. Sometimes it can be the best. And then we defined combinatorial games and proved the theorem using the Zermela's algorithm, and we looked at a very nice example of Chomp. So it's a very simple example, but you already saw some techniques from this very broad domain of combinatorial games. Much of research is actually now on parity games, and that's an infinite combinatorial game. We don't go there. It's a much more complicated thing. You, of course, don't have the Zermela's algorithm there, and that's something which is really not trivial, but I do recommend those who like this domain to take a look. So we don't go there into infinite combinatorial games. Okay.